All right, welcome back to the Kitchen Group video blogs. Today I'm going to talk about a new paper that just came out by Jenny Zan and myself. So we talked about uncertainty in a previous paper, and we build on that idea in this paper. And so the idea here is to think about uncertainty for physical properties when we derive those properties from a model. And I'll show you a couple of examples in how to think about model specific to model general uncertainty. So the paper is out in INECR. You can find it online now. And I'm going to go through the main highlights in this video. All right, so in a nutshell, when we fit a specific model, here we're going to talk about an equation of state for the energy as a function of volume, and then we will derive some properties like the minimum volume, the bulk modulus, and some things like that. And we get that from the minimum in an equation of state, or the curvature at the minimum, or some other property of the model. And we can estimate uncertainty from it, but it will turn out that that is a model-specific kind of uncertainty. And it's not the uncertainty about which model is best. And so the way we approach this is by trying several different kinds of specific equations of state and a general model that I'll talk about. And then we looked at a couple of different approaches to the uncertainty quantification for models derived from physics, models from a Gaussian process, uncertainty from the delta method, and also by Bayesian regression. And so what we found is the delta method and Bayesian regression they're pretty consistent with each other, and since they're tied to a specific model, that should make sense. And Gaussian process regression is able to kind of capture model uncertainty, which means that the Gaussian process isn't tied to a specific model, it's a general model. And the uncertainty propagation that comes out of that kind of reflects a broader sense of what the uncertainty in regard to the model and the data. All right, so the data that we looked at was an equation of state. So the data is actually shown over here on the right, and this is just the energy as a function of volume for two metals, gold and palladium, and they're just a convenient data set to use. And what we typically do is fit a function to this data. On each one of these, we stuck to this shaded area here, and then we try to derive where is the minimum from that, and the curvature here is related to the bulk modulus, and the first derivative is related to the pressure. So whatever model we fit, we derive those properties from those models, and we looked at three different kinds of regression: least squares regression for things like the Merdigan equation of state, or equivalently Bayesian regression for the same specific equations of state, and then a Gaussian process in there. So this is a snapshot of the different ways that you can estimate, say, the minimum volume. And you can see there is a range for the different models. So we have in blue here is the Gaussian process. Birch HMC is a kind of Bayesian regression on the Birch model. The dashed lines here are Birch with the delta method for uncertainty. We have a similar one for Poirier-Tarantola in Bayesian regression and the delta method. And then there's a couple of point estimates for other methods. And so you see some are very high, some are over here. The specific models may or may not overlap very much, but the blue line is the Gaussian process, and it kind of covers the whole space. It is the most general of them. So in that sense, Bayesian Gaussian process regression is a good way to do it, but I'll show you it lacks the interpretability that we get from these specific models. So in the specific models, if you're familiar with equations of state, some things are like V0, the minimum volume, and the bulk modulus are actual parameters in the model, and you get them directly in the fit. But with the Gaussian process, we have to derive them from optimization and calculus. So we made a special Gaussian process that had three components. So we were able to fit the value and the first derivative and the second derivative. And so we built in covariance matrices for all three of those components to get the highest quality model, and that way we could reliably take second derivatives of the Gaussian process. And it's interesting to me to look at this. You see the value fits visibly identical. In the first derivative, it's pretty good, but it's typical for there to be more uncertainty at the edges, and for the second derivative, you see the most uncertainty. And this is a reason why we can't really extrapolate with a Gaussian process. The second and third and higher order derivatives get more and more uncertain, and there's no physics embedded in the kernel, so the prediction outside the region that we fit just gets less and less reliable. All right, so that this figure shows that the Gaussian process in blue, if you look at this distribution for each of these different kinds of equations of state, the orange dots usually, and also the Bayesian regression in gray, often overlaps in the blue space, except for this P3. This is actually a terrible model that only works for very small ranges of volume. It's a simple cubic polynomial, and it's just not a very good model in the grand scheme of things. But for the rest of these ones that are better, the blue region shows pretty good overlap with all of the models. And so by fitting one Gaussian process and deriving these properties, you get a uncertainty that covers what other models would do. All right, so that's basically the conclusion. There are lots of ways to estimate uncertainty that have different degrees of simplicity. The Gaussian process regression provides, in our minds, the best insight on the model uncertainty, but it comes a little bit at the expense of interpretability. There are no parameters to interpret in the Gaussian process. You have to derive them from the calculus and from the math. The delta method lets you use a specific model that is interpretable, but the uncertainty then is model specific. And if you want to get a good sense of what the model general error is, you need to look at many of the errors. And Bayesian regression it's basically equivalent in our minds to the delta method, but it's much more difficult to set up and much more expensive to run. So my advice would be think about the delta method because it's very straightforward to implement, and Gaussian process regression if you want to have a broader sense. So that's it for this paper. It is really well written. Jenny did a great job, and you can learn a lot about all the different ways people think about uncertainty and regression and what the parameter estimates mean in the paper. So thanks for listening, and come back for another paper another day.